fulfills all those conditions, and we should try to do it now. So first, let us write the solutions for the field within those three regions. We have, in fact, three different regions. Inside, in between those two walls, then within the layer, and then outside up to the infinity. Those three solutions should be somehow sewed or glued at the interface so that they provide the same values for tangential components at both sides of the interface. So let's try to do that. So again, we have the system. I should possibly make one note here. We investigate a wave that is propagating into the z direction. So this is z, which was horizontal in my picture. Then we have the sketch which has the x dimension upstairs, and within this case the wave does not propagate in the direction of y. So we have turned the waveguide so that the propagation directly is reaching z infinity, and there is no deviation into the y direction. In that case, the vector ky would be 0, and we should neglect it. In fact, we did this by definition, by turning our coordinate system so that the wave does not propagate into the y direction. So this is for 3D problem. We have reduced this to a 2D problem, so we have k squared is equivalent to kx squared plus kz squared. Now we have the region 1, at which we can find the solution of the equation. Now the solution of the equation would be, or could be described in two ways. If we have a partial differential equation with constant coefficients of the second order, we have two ways to describe the solution, at least. So first way is that I would write it for S-like solution that holds both for electric, magnetic and other fields. So that S would be constant 1 e raised to minus g k z plus C2 e raised to plus g k z, or sorry, I should have written x because now I'm talking about the x direction. And this k should be kx because this is in the direction of x. So this is the first way how to describe the solution, and C1 and C2 are constants depending on boundary conditions. We could also do that in another manner. The same result, after some manipulation, could be described like a bit different constant d sine kxx plus d. Okay, we have not so far employed constant a, so a times cosine kxx. Those two solutions are equivalent, but for different boundary conditions, different versions of it could be used. Now let us choose for the inner side, for the inner layer, this solution, this part of solution. So that we will know that within the inner part we will have the electric field in the z direction given by some constant. I would call it E0. This is the transversal component of the function. We should still remember that there is the dependence on the other direction, which is this dependence is common to all fluid components because the wave has some components that together are propagating in the z direction. So this is common to any of the terms I would write later, and in order to substitute the exponential I would just make a red circle. So this is the dependence which gives us the field inside the inner layer. And we already know that we can, after some hard work, calculate all the field components that arise from it, namely electric and magnetic fields in other directions. But to be able to do that properly, we should first know Kx. That's a key component. How the propagation constant K is split into Kx and Kz. That's a key factor which we do not know so far. Now, what about the situation in the intermediate layer, or formerly the waveguide wall? Well, here, even if we here can choose one of the solutions, and let's say we will find a set of modes, so we decided to find out symmetric modes with cosine. We could also have resorted to antimetric modes with sine. So for symmetric modes we could have only one component within this. Still, in the second layer, in the wall, we will have to use both sine and cosine component. So this is the first layer solution for Ez. But within the second layer, we would have to use as equivalent to, and now we will have to use some other constants. So let's call this new constant in the second layer E21 is the second layer first constant, 1 sine Kx x plus E22 cosine Kx x. And now still remember that in fact we would have to put this into brackets and multiply by the e raised to minus jkz z. So I will, for this I have already told that I will just use the red dot. So now we have the situation in the second layer. So far we have 4 constants that we do not know. Otherwise we could already have written the result, but we do not know E0, we do not know Kx, we do not know E21 and E22. So in fact we have now 4 constants that are not known. Now let us finish this with a mark that in fact Kx and Kz and whatever is dependent on the layer. So I would now also write here that this is the constant of the first layer, this is the constant of the second layer, and I will have to include a little bit more for the third layer. I will do it before the break. So in the third layer, outside of the waveguide up to infinity, we would have to find out a solution that inherently keeps our solution bound or equivalent to 0 at the infinity. So in this case, this is not a good form, but this is. So we would have the solution for the third part of the universe we are trying to solve as Ez in the third part is equivalent to E31 and now e raised to minus jk3 x x, and of course multiplied by the dependence in the z direction. So this choice of solution for the third part of the problem, for the third layer, inherently gets us the boundary condition at the infinity. Or it could give it to us. The important point is that we should make sure that the real part of Kx is positive. Otherwise, we would have a problem. And I will get to that later. Now, please, your questions. As I can see no questions, and as we are working for 40 minutes plus, we have right for a short break. So let us enjoy a short coffee break, and a coffee possibly, and let's see again in 5 minutes.
Okay, I have a question. I am not in any team for this class.
Not really? Well, then I will try to do it, but I hope you are. I hope you are. So I will try to fix it at the end of the lecture, okay?